Hi, I'd like to give you the relationship between Kc and Kp. So you'll recall that Kp, that's going to be the equilibrium constant when we're given partial pressures of gases. Kc is going to be when we're given concentrations, so is going to be your molarity. I want you to notice something on this equation, that delta N is a change in gas moles. Change in gas moles, that's really important, that you're looking at the change of gas moles from the reactants to the products. And remember, when we do delta, we do final minus initial. So we'll take time on an example and I'll show you that. Let's see here. So looking at everything, here is our equilibrium constant for when we're given partial pressures, the Kp, equals the equilibrium constant when we're given concentrations, Kc, times R. Now we're dealing with gases here, and so it's going to be the gas constant, 0.0821, and just a reminder, atm times liter divided by mole times Kelvin, that's your unit, times temperature, which means of course temperature has to be in Kelvin, so that it matches right there. And then that delta N, again, really important, it's going to be a change in gas moles. I do want you to notice, if you have a delta N of 0, say that you have one gas mole, so 1 minus 1 is 0. Anything raised to the 0 power is 1. And so that would be Kc times 1, which means, I put it right over here, if the change in gas moles is 0, then Kp equals Kc. Well, let's go ahead and do an example. We're going to have our dinitrogen tetroxide yields 2 moles of nitrogen dioxide. And we are given that the Kc value is 4.61 times 10 to the minus 3. Remember, Kc is unitless. It is a ratio between the products over the reactants when we're at that beautiful equal rate. The rate at which the reactants change to products is the same rate that products go back to reactants. And when we're at that beautiful equal rate, forward and reverse, the Kc, notice this is less than 1, is going to be reactant favored, that you have more reactants than you do products when you're at equal rates. Okay, well, we want to know what the Kp value is. So we're given Kc, awesome, there it is. I know what R is. I'm going to go ahead and write everything down so you can see it explicitly. R will be 0.0821. The temperature, so we have 25 degrees, but we have to have that in Kelvin. So 25 plus the 273.15 gives us 298.15. Now, change of moles. So the change of moles, let's count the number of gas moles on the reactant and product sides. So product side, I have 2 gas moles, so that will be my final, 2 minus. And on the reactant side, I have 1 gas mole. 1. So you just look at the coefficients. You're looking at the coefficients of all the gas moles. If I had had another product here plus another product that was a gas, I would have counted that gas mole as well. Okay, so this is going to give us 1. The change in gas moles is 1. So let's go ahead and plug in Kp equals Kc 4.61 times 10 to the minus 3 times, and this is going to be, I'm going to put this whole thing in brackets since we have to raise that to the exponent, 0.0821 times the temperature, 298.15, and that product right there is going to be raised to the power of 1. So when we multiply this, tell you what we get, that is going to be a 24.478 raised to the power of 1, which is just 24.478. So take that, I'll leave that 1 out there, and multiply it by the 4.61 times 10 to the minus 3, and we get the Kp value is 0.1128. Okay, nice. Still less than 1, still showing that it's reactant favored. Okay, so there's your relationship. Now, for those of you who are in AP chemistry, AP has removed this. You're not going to be required to do this. It could be that a teacher would have you do it, hopefully not. But if you're in like a first year chemistry class, a Gen Chem class, good chance that your professor might have you do that. Remember this trick, I've seen this often, change of gas moles, if it's 0, then Kp equals Kc. Okay, have a good day, thanks.